In today's video, I'm going to be answering this Edexcel GCSE 9-1 chemistry paper, and it's 1 hour 45 minutes long. So, question 1. Mixtures of coloured substances can be separated by paper chromatography. Paper chromatography was used to separate a mixture of blue and red inks. A spot of the mixture was placed on chromatography paper as shown in figure 1. Give a reason why the start line is drawn in pencil rather than ink. And the whole point is you don't want that start line to be running up the paper alongside your ink splodge, because that would really screw up your results. Whereas pencil is insoluble, which means it won't move. So let's just write that here. Part 2. The chromatography paper with the spot of mixture on it was placed in a beaker with the bottom of the paper in water. On figure 2, complete the diagram showing the position of the chromatography paper with the spot of mixture at the start of the experiment. So you want your ink spot on that reference line which has been drawn with pencil, so somewhere like here. Label it ink spot. The chromatography was carried out and the result is shown in figure 3. So we can see that that single ink spot has spread out and actually contained a red spot and a blue spot, and as you'd expect, the water has flowed up the paper. The blue spot had moved 14.5 centimetres and the solvent front had moved 15.3 centimetres. So I'm going to label that here. And this distance is 14.5 centimetres. Calculate the RF value of the substance in the blue spot, giving your answer to two significant figures. That's key, make sure we do it to 2 sig fig. So luckily they've given us the equation for calculating the RF value. So that's the distance travelled by the dye, so we know that's 14.5 centimetres, divided by the distance travelled by the solvent front, which we know is 15.3. When you pop that into your calculator, you'll get a value which is 0.9477, but we need it to 2 significant figures. So we need 2 figures after that decimal point. So that 4 rounds to 5. And that is our final answer. B. P, Q, R and S are mixtures of food colourings. They are investigated using paper chromatography, and figure 4 shows the chromatogram at the end of the experiment. Which mixture contains an insoluble food colouring? So insoluble means that the food colouring or the ink doesn't move. So for it not to move, it needs to sit on the reference line, which means it's this one here, so that's Q. So we're going to put a cross on option B, mixture Q. Give a change that could be made to the experiment to obtain an RF value for the insoluble colouring. And basically, because clearly Q is insoluble in the solvent they use, you could try using a different solvent, because this might make a difference. So say you swapped water for alcohol, for example, then Q might move. And remember, solvent is the liquid. Explain by referring to figure 4 which mixture is separated into the greatest number of soluble food colourings by this chromatography experiment. So you're looking for, out of P, Q, R and S, which has the most number of dots. So we have 3 here, 3 for Q, 1 for R, and 4 for S, so the answer here is S. So we're going to write mixture S is separated into the greatest number of soluble food colourings. Why? Because we need to give an explanation, because it gives the greatest number of spots. 2. Ionic compounds contain ions. The number of electrons, neutrons and protons in 4 particles W, X, Y and Z are shown in figure 5. Explain which particle W, X, Y or Z is a negative ion, and remember here we need to remember the charge on these various particles. So electrons have a charge of -1, neutrons have no charge, i.e. they're neutral, protons have a charge of +1. So if it's a negative ion, it needs to have more electrons than protons. And so we need to look along each row and decide which here has more electrons than protons. So particle W has an equal number of electrons than protons, so it's not that one. For X, you've got 10 electrons but 12 protons, which means it's positive, so that can't be right. For Y, it has an equal number of electrons and protons, so that can't be right. So let's hope that Z has more electrons than protons. Yes, it does. It has 18 versus 16. So the answer here is Z. So right, Z is a negative ion. Because, let's just give the reason I just said, it has more electrons than protons. And you can state that Z has a -2 charge. And as by way of final explanation, you could say that electrons have a negative charge, whereas protons have a +1 charge. Calcium nitrate contains calcium ions and nitrate ions. Calculate the relative formula mass of calcium nitrate. And luckily they've given us the formula, and they've even given us our relative atomic masses. So let's write out the formula here. And to work out the MR, we need to do each of those masses added up. So calcium is 40, nitrogen is 14, but notice this 2 means we need to multiply that number by 2. Oxygen has a mass of 16, but there's 3 lots of it within the bracket, and we multiply by 2 on the outside of the bracket, so we need to multiply that by 6. And when you've done that, you get an answer which is 164. C. Lithium fluoride LiF is an ionic compound. It contains lithium cations and fluoride anions. The electronic configurations of a lithium atom and a fluorine atom are shown in figure 6. Complete figure 7 to show the electronic configurations and charges of the ions in lithium fluoride. So what happens here is you can see that this electron here has been lost. So it's lost a -1 electron, because remember electron has a charge of -1. So what will the charge be on the atom? Well, because it's lost an electron, it means it's positive, and it's positive by 1. Fluorine, we need to complete this one because this electron has gone and transferred itself to fluorine in order for fluorine to have a full outer shell. So now we need to have 8 electrons in fluorine's outer shell. And because it's gained an electron, it means it's gained negative charge, so it becomes -1. 3. A student carried out an experiment to see how reactive different metals are when they are placed in dilute hydrochloric acid. A sample of each metal was placed in a separate test tube of acid. A. When zinc reacts with dilute hydrochloric acid, a gas is given off and zinc chloride is formed. Which gas is given off? We can work this out if we write the word equation. So zinc plus hydrochloric acid forms a salt, which comes from the metal being used and the ending on the acid, so that's why it's zinc chloride, which we have been given. Plus, when you have a metal by itself, it's always hydrogen. So where's hydrogen? Well, it's option C. What is the formula of zinc chloride? So zinc has a charge of 2+, which you need to learn. Chlorine is in group 7, and to work out its charge you need to do 8 minus 7, and it's a non-metal, which means it has a minus charge. And so if you try and put these two formulae together, clearly zinc will be 2 positive. So what you have to do is work out how many chlorines you need for each zinc. So you need 2. And as you can see, that would balance in terms of charges. So if you put those formulae together, you get a formula which is this. Your teachers may have taught you the swap and drop method, so obviously use that if that works. But I prefer to show how you actually come to your answer. So anyway, the answer here is C. In the experiment, the student used the same amount of each metal in a finely powdered form. State 2 factors concerning the hydrochloric acid, which should also be controlled to produce valid results. So what do we need to keep the same about the hydrochloric acid? Well, clearly we need to use the same volume of hydrochloric acid and also the same concentration. You could also have said its temperature, it's up to you. C. Part of the reactivity series is shown in figure 8. So we've got our most reactive metal, which is magnesium. The least reactive is silver. Iron is extracted from its ore by heating with carbon. Aluminium is extracted from its ore using a different method. Give the name of the method used to extract aluminium, and hopefully you remember, because aluminium is such a reactive metal, it's more reactive than carbon, which is why this is true. You can't heat it with carbon in order to purify it. You have to use electricity, and we call this process electrolysis. Explain why aluminium is extracted by a different method rather than heating the ore with carbon. So I'm first of all going to make a statement, which is that aluminium is more reactive than carbon. And therefore, this is the real reason, therefore carbon can't act as a strong enough reducing agent. Because remember that a reducing agent is something which takes away oxygen. Because the whole point is that we're trying to remove the oxygen from aluminium oxide. And because aluminium is more reactive than carbon, you can't expect carbon to act as a strong enough reducing agent. The extraction of iron involves the reduction of iron oxide, Fe2O3, by carbon monoxide. During this reaction, the iron oxide is reduced to iron and the carbon monoxide is oxidized to carbon dioxide. Write the balanced equation for the reaction. So we have iron oxide reacting with carbon monoxide to form iron and carbon dioxide. And usually I would say balance this using the approach I taught you in a previous video. This is an annoying, super annoying equation to balance. And the easiest thing to do here, it's a bit like the photosynthesis equation or the respiration one, is to learn the numbers off by heart and try and remember that 3's are really important. So we're going to put a 3 in front of carbon monoxide. We're going to match that in front of the carbon dioxide. And then if you just have a final look, you'll see that the ions aren't balanced, which means we need to put a big 2 in front of that formula there. Just double check, you've got 3 carbons on the left hand side, 3 on the right, 6 oxygens on the left hand side and 6 on the right, so it is indeed balanced. 4. The method used to prepare a salt depends on its solubility in water. Complete figure 9 by placing one tick in each row to show whether the salt is soluble or insoluble. And I like to remember the rules here. So remember that all nitrates are soluble, all sodium, potassium and ammonium salts are soluble. So we've got ammonium here, so that's soluble. All sulfates are soluble apart from lead, barium and calcium. So we don't have any of those here, so I'm going to put soluble here. All carbonates are insoluble except from ammonium, potassium and sodium, while we have magnesium carbonate here, which is why it's insoluble. Lead nitrate solution mixed with sodium sulfate solution forms lead sulfate as a precipitate. The theoretical yield of lead sulfate for this reaction was 2.85 grams, so I'm going to write that here. The actual yield of lead sulfate obtained was 2.53. Calculate the percentage yield of lead sulfate in this experiment, giving your answer to 2 significant figures, so make sure you do that because you don't want to lose that last mark. So Percentage yield is given by the equation actual yield over theoretical yield multiplied by 100. So that would be 2.53 over 2.85 times by 100, which gives you an answer of 88.8%, and we need to round that to 2 sig figs, so the answer here is 89%. C. The method used to make the lead sulfate is: pour 100 centimeters cubed of lead nitrate solution into a beaker, add drops of sodium sulfate solution until a precipitate is seen, allow the precipitate to settle to the bottom of the beaker, pour off the liquid, use a spatula to transfer the solid lead sulfate onto filter paper. Explain 2 ways of improving this experimental method to increase the amount, so how much you get, and the quality, so how pure it is, of lead sulfate obtained from the same volume of lead nitrate solution. So if we're trying to increase the amount, where were we really limiting the amount we could make? It was just here. It was the adding a few drops, so clearly we could just add more. So let's start by saying add excess sodium sulfate solution rather than a few drops. And then it says pour off the liquid here, which is a pretty sloppy way of doing it. Really, you want to filter, so you're going to use filter paper and a funnel. So write, instead of pouring off the liquid, use a funnel and filter paper. This also enables any impurities to be removed. Hopefully, when you were learning this reaction, when you were doing your summary, you wanted to say react, filter, wash and dry. And if you don't know what I'm talking about, if you look at my video on this, you'll see that I give a very succinct, concise way of learning how to make salts, and it is in my revision guide. And look, which of these steps are we missing from this method we've been given? Well, they haven't mentioned anything about washing. So you want to say wash to remove impurities. And that's getting the marking points which are associated with the quality of the lead sulfate. And lastly, leave to dry in a warm place. So really, I'm crowbarring in my perfect answer as to how to make a precipitate into this question. D. Ammonium nitrate is produced from ammonia and nitric acid on a large scale in industry. Ammonium nitrate can also be made in the laboratory by titrating ammonia solution with dilute nitric acid. Ammonium nitrate crystals can then be obtained by evaporating off some of the water from the solution. Give 2 reasons why this laboratory method is not suitable for use on a large scale in industry. And actually, it's worth 2 marks. You need to make 2 separate points. And actually, the clues are hidden here in the question itself. Titration. If you've done this at school, you'll know that you're using a burette and a conical flask. No way could you use this method on a large scale in industry. Imagine how many burettes you'd be using, and you'd only be using about 80 centimeters cubed of liquid at a time. So first of all, volumes needed in industry are too large for the titration method. And it also says here that the ammonium nitrate crystals can be obtained by evaporating off some of the water. So you've basically got to allow them to crystallize. Well, it's going to be very, very difficult when you've got huge amounts of liquid and crystals forming to actually allow those to crystallize, to evaporate off some of the water. So that's going to be your second point. 5. Objects made from transition metals are sometimes coated with a thin layer of another transition metal to improve their appearance and to protect against corrosion. Figure 10 shows equipment that can be used to electroplate an iron spoon with silver. Which row of the table correctly shows the charge on the silver rod electrode and the type of reaction occurring at this electrode? So remember, the thing you need to remember with electroplating is that first of all, the thing being electroplated, so the thing being covered with the favourable, useful metal, is always the cathode. And according to Pank, it's positive anode, negative cathode. So we know that the cathode here is negative. Because it's electrolysis, we need both a positive and negative electrode, which means automatically the silver rod is positive because it's the anode. And also taking place is the fact that those silver atoms on the silver rod will get oxidized in order to form this solution of silver ions. So when something gets oxidized, it loses electrons. So it looks something like that. So if we look at the options, we're looking for the silver rod being positively charged because it's the anode, and we know that oxidation is occurring here. So the answer here is C. Silver metal is deposited on the spoon. Which half equation represents this equation? So silver metal, so not an ion, silver metal is being deposited, which is why it's on the right hand side. It's being produced from silver ions, and they have to gain electrons, so be reduced in order to do that. Look down the list and see which option matches that, and you will see that the answer here is C. Voltage of the cell is 1.5 volts. Give a reason why this voltage of the cell decreases when the cell is left connected in a circuit. And that's simply because those silver ions in solution are being reduced, so they actually leave the solution. So actually there are fewer reactants available. Duralumin is an alloy of aluminium and copper. The radii of the aluminium and copper atoms are shown in figure 11, so we can see here that copper is smaller than aluminium. Explain why copper added to aluminium to form the alloy makes the alloy stronger than pure aluminium. So first of all, state what you can see from the table, which is that the aluminium and copper atoms have different sizes. And remember, when you go from having a metal with a regular shape like this, so pure aluminium, to one which has different sized atoms like this one, which is very similar to what we're looking at now, you find that those different sized atoms distort the layers, meaning that the layers can no longer slide over each other. Gold is often alloyed with other metals when it's used to make jewellery. The proportion of gold in a piece of gold jewellery is measured in carats. Pure gold is 24 carats. A 9-carat gold ring has a mass of 12 grams. Calculate the mass of gold in this ring. So first of all, you need to work out the proportion of gold in the ring. And you do that by getting 9 and dividing it by 24, because we have a 9-carat gold ring and pure gold is 24 carats. So once you've done that, you know that your proportion of gold is 0.375. And then to work out the mass, you have to multiply that by the mass of the ring. So you do 0.375 times by 12 to get 4.5 grams. So of that 12 grams of ring, only 4.5 of it is actually made from gold. 6. Electrodes are placed in different solutions J, K and L. A 6-volt direct current source is connected to the electrodes. Any products formed at the electrodes are identified. The results are given in figure 12. Explain which solutions are electrolytes. So electrolytes are ones which conduct electricity, and so that will be J and K, according to these two yes answers. Which material is most suitable to make the electrodes for the electrolysis of our dilute acid? Remember, you want an unreactive or inert substance, and we tend to use graphite or metals like platinum. Have a look down this list and you can see that graphite is one of the options, so I'm going to cross that one there. When a solution of sodium sulfate, Na2SO4, is electrolyzed, the products formed at the electrodes are hydrogen and oxygen. Explain the formation of the products at the electrodes. So let's have a look first of all at the ions which would be present in the solution. Now, because we're looking at a solution, we know that H plus and OH minus must be present. And then looking at the substance in question, so the sodium sulfate, this also means that there must be sodium ions and sulfate ions present. Now, in terms of which of these ions discharges, let's take the negative electrode first of all, which is the cathode. So let's write negative electrode. Obviously, it's going to be a positively charged ion which will discharge because opposites attract. So you're picking between hydrogen and sodium, and you must remember that the least reactive element discharges. So hydrogen ions are attracted because they are oppositely charged and less reactive than sodium. And we can even write the summary equation for the formation of hydrogen. So H plus plus E minus forms H2, which is diatomic, so we need to balance. And now we need to look at the anode, which is the positive electrode. Remember, if you have a halogen present, then that will discharge preferentially. However, sulfate ions and hydroxide ions are not halogens, which means that the hydroxide ion discharges, forming oxygen. So let's write that here. And why are they attracted to the positive electrode? Well, for the same reason as before, because they are oppositely charged. And because this is worth 4 marks, it's worth writing out the equation, which is 4OH minus produces water plus oxygen plus 4E minus. And that is a very full answer indeed. Copper is purified by the electrolysis of copper sulfate solution using an impure copper anode and pure copper cathode. Write the half equation for the formation of a copper atom from a copper ion. So on our reactant side we need a copper ion. We're forming a copper atom. So how do we get a neutral atom? Well, we need to add negativity. So we're going to add 2E minus. 7. Sulfur trioxide is produced by reacting sulfur dioxide with oxygen according to the equation 2SO2 plus O2. This is a reversible arrow forming 2SO3. The reaction takes place in industry at 1 to 2 atmosphere pressure and can reach a dynamic equilibrium. Explain the effect on the rate of attainment of equilibrium if the process is carried out at a pressure higher than 1 to 2 atmospheres. So notice that the question is asking about the rate of attainment of equilibrium if you increase the pressure. So it's not actually asking you about the position of equilibrium, it's actually a collision theory question. So it's really asking what is the effect of increasing the pressure on the rate of reaction, and clearly the rate will increase. So let's first of all make that statement. So rate of attainment of equilibrium increases. And why? Well, and that's really because there are more gas molecules present, and therefore collisions will clearly occur between the reactant gas molecules more often. What volume of oxygen in centimetres cubed would react completely with 500 centimetres cubed of sulfur dioxide? And in order to answer this question, you need to look at the mole connection. So you need to look at these large numbers here. And as you can see, 2 moles of sulfur dioxide react with only 1 mole of oxygen. So really you only need half that number, which is why the answer here is A. When there are alternative methods of producing a product, the final pathway is chosen by considering atom economy, cost of energy, yield of products, and rates of reaction. State another factor that should be considered. So use your common sense here. let's actually think when we're looking at a product, what is it we're after? Well, you might want to look, if it's a reversible reaction, at where the position of equilibrium lies. And again, if there are side reactions taking place, you might want to have a look at how useful those byproducts would be. So either one of those answers would be suitable. C. The reaction between nitrogen and hydrogen is exothermic, which means it gives out heat energy. If nitrogen and hydrogen were reacted at 150 atmosphere pressure and 300 degrees Celsius without a catalyst, some ammonia would be formed. In the Haber process, a pressure of 150 atmosphere and a pressure of 450 degrees Celsius are used in the presence of an ion catalyst. Explain why the conditions used in the Haber process are better than the first set of conditions for the manufacture of ammonia. Okay, so there's a lot to unpick here first of all. So let's first of all look at the fact that the reaction is exothermic. Because the forward reaction is exothermic, meaning that it gives out heat energy, really you want to lower the temperature. So first of all, we're going to state that really a lower temperature should be used because the forward reaction is exothermic. But what's the problem with low temperatures? Well, it means that the rate of reaction is too low because it means the reactant particles have little kinetic energy. So that's why we actually increase that temperature to 450 degrees. So let's state that now. However, we use 450 degrees Celsius because it provides reactant particles, or let's just call them nitrogen and hydrogen, with greater kinetic energy so collisions occur more frequently. Let's have a look now at the pressure. Well, they haven't said too much about the pressure. You can simply state that high pressures give high rates of reaction. What I'm really interested in looking at now is the ion catalyst. Why do we like to add an ion catalyst? Well, that's because it increases the rates of reaction. And crucially, annoyingly, it's both the forward and reverse reaction. Let's state how the catalyst works by providing an alternative reaction pathway. With lower activation energy, and that's something you need to learn. That's how a catalyst works. Notice that there is no effect on yield. And that is of ammonia. So that's quite a full answer to get those 6 marks. Question 8, figure 13 shows a model of how particles are arranged in a solid. State 2 ways in which this model fails to represent a crystal of sodium chloride. Well, notice we've got 2 elements here, so it's likely that they'd have different sized atoms. And lastly, remember, because sodium chloride is a giant ionic lattice, it means it has a complex 3D crystalline structure, which I can't really draw, but it looks something like this. So 3D, whereas this is obviously 2D. Part 2. Magnesium oxide has a melting point of 2852 degrees Celsius. Explain why magnesium oxide has such a high melting point. This is where you have to learn all the answers as to why metals have high melting points, why giant ionic structures such as this one have high melting points, why simple covalent structures have low melting points, and finally why giant covalent structures have high melting points. You really must learn these answers off by heart, and I'm about to show you the perfect answer for giant ionic lattices. So let's start by writing MgO is a giant ionic lattice. And let's really state what that means. So made up of strong electrostatic forces of attraction between oppositely charged ions. And let's state what those ions are. So Mg2 plus and O2 minus. And really, these strong electrostatic forces of attraction require lots of energy to break. Hence why magnesium oxide has such a high melting point. Carbon dioxide can be formed by the reaction of calcium carbonate, CaCO3, and dilute hydrochloric acid. Write the balanced equation for this reaction. So our reactants are calcium carbonate and hydrochloric acid. CaCO3. You should know that hydrochloric acid has a formula of HCl. The name of the salt formed, well, we take it from the metal and the ending on the acid, so that's going to be calcium chloride. Calcium has a 2 plus charge, chlorine has a 2 minus charge. Chlorine, has a 1 minus charge, so really you're looking for 2 chlorides, so that's why the formula of calcium chloride is CaCl2. And then we're going to produce, we've been told, carbon dioxide as a byproduct, and lastly water. Double check, does it need balancing? Well, you've got 2 chloride atoms on the right hand side, only 1 on the left, so you need a big 2 there, and that is done. The thermal decomposition of copper carbonate forms copper oxide and carbon dioxide. 15 grams of pure copper carbonate is decomposed completely. Calculate the mass of solid produced. Give your answers to 2 sig fig, so we must do that. So this is how I'm going to do it. I'm going to write out my balanced symbol equation again. If you've watched my mole calculations, then you know I love a table format. And we're going to write the formula triangle we're going to need up here. So that's mass, MR, number of moles, and we're going to label our table with the same tags. So we've got 15 grams of copper carbonate, which is why I'm writing 15 here. We're looking for the mass of solid produced, which we can see from the balanced symbol equation above is going to be this substance. Next up, we want to calculate the MR, so we're going to use these numbers here. So really you're going to do copper, which is 63.5, plus carbon, which is 12, plus 3 times 16 in order to work out the MR of copper carbonate. So that gives you an MR of 123.5. Let's do the same now for copper oxide. So that's just 63.5 plus 16, which is 79.5. To work out the number of moles of copper carbonate, look at your formula triangle. You want to do mass divided by MR. So let's do that now for copper carbonate. Do 15 divided by 123.5 to get a number of moles, which is 0.12145. And then have a look at your mole connection here. As you can see, that it's the same. It's 1 to 1 to 1, which means you're allowed to just copy this number directly over. And now look, you're missing the mass, but we know how to calculate mass from our formula triangle. We do MR times number of moles. We've calculated the MR as being 79.5, times it by the number of moles, which is 0.12145. And once you've done that, you will get a value which, once rounded to two significant figures, is 9.7 grams. C. Magnesium reacts with water in the form of steam as shown in the equation. 2.4 grams of magnesium reacts with sufficient steam for a complete reaction to form 5.8 grams of magnesium hydroxide and 0.2 grams of hydrogen. Show by calculation that the law of conservation of mass applies to this reaction. So in order to do this, really we need to show that the mass of reactants equals the mass of products. And the mass of products is easy to work out because we've been told that we have 5.8 grams of magnesium hydroxide, 0.2 grams of hydrogen. So if you add those together, you're going to have 6 grams. However, from the reactant's point of view, we've only got 2.4 grams of magnesium and we don't know how much water we've got. So really, we need to show that that X is equal to 3.6 grams. So we're going to have to do a mole calculation in order to prove that. So let's write out our balanced symbol equation. Here's the formula triangle we're using. So mass, MR, number of moles. So we're really looking for the mass of water, so that's why we're putting an X there. Doesn't matter which other number we use, but just because it's easy, I'm going to use 2.4 grams of magnesium. So the MRs we've been given in the question. So for magnesium, it's 24. For water, ignore the big 2. You're just doing 2 lots of hydrogen, which is 2 times 1, plus oxygen, which is 16, added to 2 makes 18. And then lastly, number of moles. So according to the formula triangle, we do mass divided by MR. So 2.4 divided by 24 is 0.1. Now check the mole connection. It's 1 to 2, which is why we need to multiply that number we've just calculated to work out the number of moles of water. So that's 0.2. And then do 18 times 0.2, which is 3.6, which is great because basically we're saying that the mass of reactants equals 2.4, so that's the mass of magnesium, plus 3.6, which is the mass of water, to get 6 grams, and the mass of products, as I've already said, is 5.8 plus 0.2, been given that in the question, and that they're the same. So conservation of mass applies. Some acids, such as hydrochloric acid, are described as strong acids. Some acids, such as ethanoic acid, are described as weak acids. Explain the difference between a strong acid and a weak acid, and that's all to do with how readily the acids give up their hydrogen ions. If they fully dissociate and produce lots of hydrogen ions, then you have a strong acid. If you have a weak acid, they do not readily ionize. So let's write this. That's an F. A weak acid only partially dissociates. Give a reason why adding hydroxide ions to an acid solution leads to an increase in pH. And what you find is the hydroxide ions react with the hydrogen ions, thereby reducing the hydrogen ion concentration. And if you have fewer hydrogen ions, then you have an increased pH. The salt zinc nitrate can be made by reacting zinc oxide with dilute nitric acid. Write the balanced equation for this reaction. So we've got ZNO reacting with nitric acid HNO3 producing zinc nitrate. So Zn has a charge of 2+, Nitrate has a charge of NO3-. Hopefully you can see that Zn is 2 positively charged, so we need a second NO3-. The way in which we have to write that is a bracket surrounding the NO3, just so that we can pop that 2 down on the right hand side. And then because it's an oxide reacting with acid, we produce water as a byproduct. And now we need to check that it needs to see if it needs balancing. Yes, it does. There are way too many nitrates on the right hand side, so too many nitrogens, too many oxygens. So we're going to add a 2 here to try and balance that. And yes, if you have a look now, you'll see that that is balanced. 50 centimetres cubed of potassium hydroxide solution of concentration 40 g dm to the -3 is needed for an experiment. Calculate the mass of potassium hydroxide that must be dissolved in water to make 50 centimetres cubed of solution of this concentration. So have a look at the units when you're answering this. It's per decimeters cubed, which is why you need to take that 40 and divide it by 1,000. And then we're making up a specific volume, which is 50. So we multiply that number by 50 to get a value of 2 grams. D. Salts of metals can be made by reacting one of the metal's compounds with the appropriate acid. Plan an experiment to prepare pure dry crystals of magnesium sulfate, MgSO4, by reacting a suitable magnesium compound with a suitable acid. You may use equations if you wish, so it's probably worth popping in some equations there. And look, we're trying to produce magnesium sulfate. So notice that this is a soluble salt. So in terms of our metal compound, doesn't really matter which one you pick, but I'm just going to pick magnesium oxide. So I'm going to write react magnesium oxide with a suitable acid. So let's have a look at the salt we're actually after. Well, it's sulfate, so we're going to obviously have to use sulfuric acid. If it said magnesium chloride, we would have used hydrochloric acid. So react magnesium oxide with sulfuric acid. And then once you've reacted them together, you need to get rid of the excess solid. So you want to filter off the excess solid. Using filter paper and a funnel. And then at this point, because you're making soluble salt, you need to evaporate some of the water. And lastly, we need to leave to dry. So leave to dry and state in a warm place or on a filter paper. Because it doesn't look a very full answer, I'm now going to write my equations. So we're reacting magnesium oxide with sulfuric acid to form the salt, which they've given us the formula MgSO4. Water is produced as a byproduct. Double check to see if it's balanced, and yes, it is balanced. 10a. In an experiment, ammonia gas is made by heating a mixture of ammonium chloride and calcium hydroxide. 10 grams of ammonium chloride is added to an excess of calcium hydroxide. Calculate the maximum volume of ammonia gas that could be formed. Okay, so I feel like this is a lot of work for 2 marks. I don't really understand their mark allocation. So let's start by writing out the balanced symbol equation. My table as usual. Okay, so first of all, we're told that we have a mass of ammonium chloride, which is 10 grams. And we're looking for the volume of ammonia. So I'm going to just write that over here so I know what I'm doing. Let's work out our MR of ammonium chloride. So that's going to be 14 plus 4 times 1, which is the mass of hydrogen, plus 35.5 to get a value of 53.5. You ignore this 2, don't worry about that now. To work out the number of moles, we do 10 divided by that number, because it's mass divided by MR, to get a value which is 0.186915. You want to keep that number unrounded because you don't want to add rounding errors here. Then have a look at our mole connection now. It's 2 to 2, so actually we're allowed to steal that number and say that that is actually the number of moles of ammonia. And then lastly, to work out the volume of ammonia gas, it's really straightforward. You just take that number of moles and multiply it by 24. because 1 mole of any gas occupies 24 decimeters cubed. So that's why you're allowed to do that. You must remember that number, it's really key. So you get 4.49 decimeters cubed, and we just need to double check and have a look at the units. Yeah, it's decimeters cubed, so that's actually the correct answer. Sodium hydroxide solution reacts with hydrochloric acid. 25 centimeters cubed with 0.1 molar sodium hydroxide solution is added to 35 centimeters cubed of 0.075 molar dilute hydrochloric acid. Use the information to determine which reagent is in excess. So, writing out the equation yet again, you'll need a different formula triangle this time because you've got concentrations here and you've got volumes here. So you need this formula triangle, which states the number of moles is concentration times volume. And because you're looking for which reagent is in excess, this is how you're going to do it. So a table again, this time with NCV. Let's just take one lot of information first of all. So we have 25 centimeters cubed of sodium hydroxide. We need to divide that by 1,000 in order to convert it to decimeters cubed. Do watch my videos on mole calculations, titration calculations if you're not sure what I'm doing here. Then we've got a concentration of 0.1 molar sodium hydroxide. So I'm hopeful here that you can see that we are now ready to work out the number of moles using our formula triangle. So just do 25 over 1,000 times 0.1 to get a number of moles, which is 2.5 times 10 to the minus 3. And actually what you want to do here is carry that number across as being the number of moles of hydrochloric acid. Okay, and that's done. Now go back to the original question and do the same but with this second number. So we're going to really work out the number of moles of hydrochloric acid by doing concentration, which we've been told is 0.075, times the volume, which we've been told is 35. Don't forget to divide it by 1,000 because we need to convert it to decimeters cubed. And you get 2.625 times 10 to the minus 3. So those are actually the amounts we have. So just have a look. We have an amount, we have a number of moles of sodium hydroxide of 2.5 times 10 to the minus 3. And based on this calculation here, we know that we only need 2.5 times 10 to the minus 3 moles of hydrochloric acid. However, in actuality, we've got 2.625, so we've got more hydrochloric acid than we need, so that's why hydrochloric acid is in excess. To find the exact amount of dilute hydrochloric acid that reacts with 25 centimeters cubed with a sodium hydroxide solution, a titration is carried out, and figure 14 shows the results for the titrations. In this titration, the accurate volumes of acid used are within 0.20 centimeters cubed of each other and are considered concordant volumes. Use the concordant results to calculate the mean volume of hydrochloric acid required. So we are looking at the hydrochloric acid required, so that is this line here. And let's double check that the results are concordant. So they need to be within 0.2 centimeters cubed of each other, which means this is concordant and this is concordant. So let's add those two together and then divide by 2 to get a mean or an average. And once you've done that, you get a value which is 36.25. During the titration, the indicator used changed colour at the end point. Which of the following shows an indicator with the colour change that would be seen in this titration? This is something that you'll quite simply have to learn, all these colours of indicators, but it's worth knowing that methyl orange is yellow in alkali and turns orange when it's in acid, so that's why the answer here is D. In another titration, 25 centimeters cubed of a different sodium hydroxide solution is titrated with 0.2 molar sulfuric acid. 24.8 centimeters cubed of acid are required to neutralize 25 centimeters cubed of sodium hydroxide solution. Calculate the concentration of sodium hydroxide solution. These questions are all quite similar. I don't understand why this one is worth 4 marks. Let's do number of moles, concentration times volume. Write out our balanced symbol equation. So NCV, and now we're just going to go through and identify the various numbers. So we've got 25 centimetres cubed of sodium hydroxide, so that's going in here. Remember to divide it by 1,000 to make it into decimeters cubed. We've got 0.2 mole of sulfuric acid, so that is its concentration. We've been told that 24.8 centimetres cubed of the acid are required, so that's why this value goes in here. We're going to divide it by 1,000 again. And lastly, we're looking for the concentration of sodium hydroxide, which is why the X sits here. We're ready to get going. So first of all, we're going to look for the number of moles, because we've got two numbers in that column already of sulfuric acid. So looking at our formula triangle, we just need to do concentration times volume. So that's 0.2 times 24.8 divided by 1,000 to get 4.96 times 10 to the minus 3. Check the mole connection. It's 2 to 1, so you need to multiply that number by 2 to get the number of moles of sodium hydroxide. So that's 9.92 times 10 to the minus 3. And now we're only missing the concentration of sodium hydroxide. So concentration is number of moles divided by volume. So 9.92 times 10 to the minus 3 divided by 25 over 1,000. And you'll get a value which is 0.397, and make sure you've got the correct units here. And we're done. That was quite a beast of a paper. Why don't I just write that number in here for completeness sake? Right, hope you found that talk through really helpful, guys. I'll be back soon with a biology talk through. Don't forget to sub and tell your friends about my channel.